All right, let me pay the TA. Are there any questions to start with? I'm a little surprised there were no questions because the material we were discussing last time was a little bit confusing.
Too confusing to ask questions. It's too confusing to ask questions. I'm very confused about it.
All right, well, I guess that's sort of a question.
Oh, that's the first one I dropped.
I'm throwing them faster and faster. I hope you don't mind. I'll try to slow down. Let's see if I can give a kind of overview of what we did last time. The key thing, I suppose, is that if we have a free field, then it evolves in time this way. In other words, H0 is the free Hamiltonian, and H0 is the free field. Now, sometimes I'm going to leave the zero off the free field if we're basically in free field land. Okay. On the other hand, the full field, the fully interacting field, evolves in time this way. So these are said to be Heisenberg fields. I'm not big on these names and these pictures, but anyway, they evolve according to the Hamiltonian of the theory. And if we're in the full theory, then it's H, and if we're in theory we can actually cope with, say, H0. All right, now, what we normally say is that phi of x and 0 is the same thing as phi 0 of x and 0. In other words, the idea is that the free field and the interacting field, we imagine that they're the same at some time, time 0. At least in the simplest way of looking at things. And we could say the same thing about the momentum conjugate to the field. That these are the same at time 0. And what this means then is you can, of course, make the annihilation and creation operators of the free theory out of these two operators at time 0. And you can then make the annihilation creation operators, the interacting theory at time 0, out of these operators. Okay. So now if we imagine what things are like way back in the past, and when I think of way back in the past, I tend to think of before the dinosaurs. But of course, if you're talking about a collider experiment, it means, femtosecond before. Well, yeah, easily a femtosecond. A femtosecond because the speed of light is, isn't it a femtosecond per foot?
Sure.
Femtosecond, 10 minus 15 seconds. Speed of light is 3 times, well, anyway, let's not work it out. It's something, the speed of light is a foot per something. Is it picosecond?
Anyway. God, I'm really regretting that this meeting.
Okay, so the point is, though, that these annihilation operators of the free theory for any particular momentum annihilate the free vacuum, and they would also annihilate the free vacuum in earlier times, or at any time, because the free vacuum just goes as, it's an eigenstate of H0, so you have e to the minus I, E0t. E0 is typically 0. And so what we can imagine then is that this let's see, the trouble is I'm doing this without notes rather than following my notes, and so let me try to get to my notes. All right, so let's anyway, this is in fact 0, and we could then say that let me get I'm trying to make this simpler, but I see I'm actually making it worse. We could say e to the minus I H0 t would be 0, and on the other hand, we could say a of p e to the minus I H t on the fully interacting vacuum is 0. So this for big T, this brings the vacuum so these two operators are the same at time 0, and since they annihilate the same state, what we can say is that the interacting vacuum is an e to the IHT, e to the minus I H0t on the vacuum of the free theory, apart from perhaps an overall constant. So it's proportional, and the idea is that we've basically got two vacuums. We've got the interacting vacuum at before the collision and then after the collision. And these would be limits as t goes to minus or plus infinity for the basically the in and out states. The Weinberg's picture of this is that in the far past, you've got particles coming into each other like this, and then in the far future, you've got particles, and in fact, far, as I said, is a picosecond or something. And now, if we're talking about the free theory, then we don't really need wave packets because the particles don't interact at all. But if we're talking about the interacting theory, we need to surround these particles with wave packets so that they don't, so that the wave packets then restrict the particles to areas. Before and after the collision, they restrict the particles to areas of space that are far from each other, and so they're not actually interacting. And in Weinberg's view, what you've got is e to the minus IHT on alpha is his way of saying integrate over all momentous, sum over the spins, and so forth. G of alpha are the wave functions. Then alpha plus or minus are these in states of the interacting theory. If it's plus and minus means the interacting states in the future. And so these are eigenstates of the full Hamiltonian. So this is a d alpha, g of alpha, e to the minus I, e alpha t, alpha plus or minus. So these are the interacting ones. And then the idea is that if we take the limit as t goes to minus or plus infinity, then what we're getting is the same thing in some sense as the limit t goes to minus or plus infinity of d alpha g of alpha e to the minus e alpha t of this eigenstates now of the free theory. And what we do here is we arrange that the eigenstates of the free theory, the single particle eigenstates of the free theory, have the same energies as the single particle eigenstates of the interacting theory. And that means that when we talk about the free theory, we give the electron its correct physical mass, we give the positron its correct physical mass, same as that of the electron, and so forth for any of the particles that we're dealing with. And even if we have a composite theory, a composite particle in the interacting theory, then we need a composite particle in the free theory of the same mass. So we need an alpha particle in the free theory, even though we don't have any interactions to hold the protons and the neutrons together in the free theory. Okay. So the idea is that H0 on alpha is E alpha alpha, and H on alpha plus or minus is E alpha alpha, because these plus minus states are ones that we're thinking of they would be multi-particle states, but the energy we're giving them is the sum of the single particle energies. And the reason is that we're thinking of them only as separated because of the wave functions. And so, in view of this, what we have is that alpha plus or minus inside a wave packet is e to the IHT e to the minus I H0 t alpha as t goes to minus and plus infinity. And Weinberg's notation for that, unfortunately, is omega minus plus of t, t being large number alpha. Okay, so that means that the vacuums, the in and out vacuums of the interacting theory are e to the IHT, e to the minus I H0 t, on that of the Bayer theory, again, as t goes to minus or plus infinity. And Schwartz has the same formula. He puts in an overall proportionality constant or phase factor there. And so if we look at it in Schwartz's term, it's omega minus is some ni lim t goes to minus infinity e to the I h t e to the minus I h 0 t on 0. And if we consider this in the future, then it's some other factor, t goes to plus infinity, again the same thing, e to the I h t e to the minus I h 0 t on the Bayer vacuum. And another way of thinking of this is that basically the S matrix is omega big T, omega minus big T, and this is e to the I h0t, e to the minus 2I th, e to the I h0t. And in Schwartz's notation, that is effectively u of big T minus t. And here then u of t and t0 is e to the I h0t, e to the minus I h t minus t0, e to the minus I h0 t0. And now, as we saw last time, I du dt, we can bring down an I h0 here, and we bring down a minus I h here, and the difference of the two is v, but the v is sandwiched in here, so we have e to the I h0t, v, e to the minus I h0t, and then we have u of t and t0. And then we call this then is the interaction, but it's the interaction, but with the free field time dependence, or the time dependence of the free Hamiltonian. So we call that v of t. One might put a 0 on it, and then u of t and t0. And now this is an equation that has a natural solution in terms of time ordering. In other words, u of t and t0 is the time ordered product of e to the minus I integral t0 to t, v of t prime dt prime, where v of t prime is this with a prime on the t's. Okay, so what we've got then is, and all right, let me back up a little bit because there's a little bit of bookkeeping that we have to do now. And so let me say here that we have T1 greater than T2 dot dot greater than Tn. And now we want omega T phi of x1, phi of xn. I think I'm going to stop using these squiggles because I find it really hard to write squiggles. So I'm just going to write ordinary parentheses. Yes.
So, I guess I'm a little confused here about this interacting vacuum and the Bayer
You
vacuum.
want a candle?
No, I'm okay. So, are we sort of saying that because we have this interaction theory, we can't calculate the vacuum state exactly, and so we use this kind of a technique to give some kind of approximation to it, that we can then use in these later formulas as sort of a given.
Yeah.
Okay. And we should think of it then as evolving the bare vacuum forward in time under its Hamiltonian, and then evolving that backwards in time.
You can think of it that way, yes. Or taking the bare vacuum that we understand at time zero and evolving it backwards in time with t0 and then forwards, or I think maybe your way is better. Anyway, yes to what you said. All right, in this case, this thing is just omega phi of x1 dot 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 phi of xn, because the points are in time order to begin with. And now we re-express the vacuum. In fact, I should have said this is a final vacuum, initial vacuum. And so this is then Ni NF, although there might, well, all right, Ni NF vacuum. And now what evolves everything forward is U infinity 0, U0, 1, phi 0 of x1, U1, 0, U0, 2, phi 0, x2, U2, 0, and so forth. U0n, phi 0, xn, Un, it's an n, 0, U0 minus infinity 0. So this gives you, this together with the factor gives you omega at minus infinity. This with the NF gives you omega at plus infinity. And then these factors, this takes the free field at time t1 into the interacting field at time t1. Because with U, what you've got is you've got the IH0 first that undoes the free time dependence, and then the e to the minus IHT, which does the fully interacting time dependence. And now, what this turns out to be then is NINF 0, and now we see this is just U infinity 1, phi 0 at x1. And now this guy is, well, this is U1, 0, U0, 2, that's U1, 2. And then we have phi 0 of x2. So the phi's here have the free field dependence. And then you have U2, 3, dot, 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 UN minus 1 n, phi 0 xn, UN minus infinity 0. Okay. And so now this thing is if we put back in time ordering, it's 0, time ordering, and we can take the two U's and put them together at the end, because we have time ordering, we don't care where we put things. The time ordering fixes everything. So this is the product of the fields. Oh, that was bad parenthesis. All right, what we have then here is U infinity minus infinity, n parenthesis 0. On the other hand, if we look at this expression without any field, then we have omega f, omega I equals ni nf, 0, time ordered product, well, doesn't really matter at this point. So this NINF is, all right, and this we're thinking of as one. That is to say, the inner product of the two physical vacua, let's suppose that the energy of the physical vacuum is 0, then any phase factors associated with time evolution would, well, just be 0 in the answer. And so what we get is NINF is 1 over 0 time ordered u infinity minus infinity 0. All right. And now we remember what u of infinity minus infinity is. It would just be this time ordered product of the integral from minus infinity to plus infinity. So at this stage, what we have is omega t phi x1 phi xn omega is free vacuum, time ordered product, all the fields, free fields, or fields with free field time dependence. Keep putting that thing there. U of infinity. Well, that U of that big U is e to the minus I integral minus infinity to plus infinity d of t prime dt prime closed time dependent 0, and then we have to divide by 0 time ordered product e to the minus I integral minus infinity plus infinity d of t prime dt prime 0. So that's our expression. And what's nice now is that this V is actually, it's the difference between H and H0. And so that's minus the integral of the interaction Lagrangian over space. And now we're told we have to integrate it also over time. And the minus signs cancel. And so our expression now is 0 time ordered product fields. I'll just write it this way. E to the I integral the interaction of Lagrangian d4 x closed time order in 0, and then we divide by 0 time order e to the I integral li d4 x 0. All right, so that's the bottom line. That's the thing you want to remember. So simple vacuum here, simple vacuum there. Time ordering, free fields, interaction Lagrangian with the free field time dependence, same thing here. And in principle, if instead of being people, we were computers, we'd look at this and say, wow, and we'd compute all the cross-sections instantly, because there's no mystery left in this. It's just tedious computation. Because it turns out that the Feynman propagator that we did last time is the whole story for evaluating this thing. Fortunately or unfortunately, we're not computers. And so when we look at this, we say, oh! And that certainly is the way I feel. There is a nicer way of thinking about this, namely in terms of path integrals. In that case, this thing is a ratio of path integrals. And there, it just looks so much nicer. And of course, the path integral formulation is useful for seeing things from one point of view. This formulation is good for seeing things from a different point of view, and it's good to have both points of view. Some people go to the extreme of leaving out the annihilation creation approach, the free field theory approach. This approach that we've been following, some people, Strednicki just throws it into the trash and starts with path integrals. But I think Schwartz is right to do this first. That's what Weinberg does also. So, as an example,
If v of t might be an integral d cubed x lambda over 4 factorial phi 0 to the 4th at x and t. And so what we would have there would be that u of infinity minus infinity would be time ordered product e to the I lambda over 4 factorial integral d4 x phi 0 to the 4th of x, where again this has the free field time dependence. All right.
okay, I think that's enough of that. Now, okay, now it's conventional to take this free field and to separate into what used to be called the positive frequency part and the negative frequency part. And the trouble with the positive frequency part is that it went as e to the minus I omega t, and the negative frequency part went as e to the plus I omega t. And Schwartz decided, probably wisely, to break with the tradition. And he has then phi plus of x is integral d cubed p 2 pi cubed a daggers of p. This is we're talking free fields here, so everything is free fields from now on essentially. 2 omega p e to the I px. This is Lorentz, however. So this is omega pt minus p dot x times I. But just the creation operators, and so this, which used to be called the negative frequency part, he calls phi plus. And so the plus goes with that plus sign. This makes sense. Phi minus of x is then integral d cubed p 2 pi cubed a of p square root of 2 omega p e to the minus I px. And the full field phi of x, or at least the free field, is phi plus of x plus phi minus of x. Schwartz may have an extra 0 here. So we're now in free field land. And so let's, I don't think it helps to have zeros everywhere, because it just makes the notation worse than it would be. So to translate between what I write and what is in Schwartz's book, add zeros everywhere. Okay, so he chooses to look at a particular term. In other words, when we have this expression here, suppose our Li was lambda over 3 factorial, or g over 3 factorial phi cubed. Then we would have various terms. I just wonder whether I skipped a page here. Yes,
Are they numbered?
they are numbered.
Ah.
Yes, I skipped the top of the page. All right, so let's then look at this particular, we're in this particular theory, 5x1, 5x2, e to the I, d4th x, li, 0. Okay, so this is the full, this would be the thing that, or the numerator of what we would be, this is this numerator, okay? But for the case where we only have two fields. All right. Now we're going to do, not only are we in free field land, we're going to do perturbation theory. So we expand this thing. The first term is 1. And so the first term is 0t of 5x1, 5x2, time ordered. And we know what that is. That is Feynman's propagator that we worked out twice. Next term is I, assuming that here I've taken Li as g over 3 factorial phi cubed. I then g over 3 factorial and integral d4 of x, so it's the first term here, and it would be 0 time ordered product phi x1, phi x2. Remember, these are free fields, so there are zeros missing. Phi cubed of x, 0. So that's the second term. Now this term is 0. Why is it 0? It's 0 because we're starting with the vacuum. We've got to get to the vacuum. And the only way to do that is to create and annihilate the same number of particles. But each field either creates or annihilates. So there's just no way to get from there to there when you have an odd number of fields. At least an odd number of neutral fields. They're charged, I'd have to think again. Probably couldn't do it then either. Okay, the next term is ig over 3 factorial squared. This is a 1/2 from the sum of the exponential, and we get d4 of x, d4 of y, 0 time ordered product, free field at x1, free field at x2, cube of the free field at x, cube of the free field at y, 0. And now the thing to do is to replace each field with phi plus phi minus. If you do that, then the fact that this is 0 becomes more transparent, because what you have here then, maybe I should, shall I show explicitly why this is 0? I'm getting a no vote there.
I'll say yes, just to be contrarian.
Ah, contrarian. Okay, so let's look at why this is 0. It's 0 time ordered product, creation plus annihilation, creation plus annihilation, creation plus annihilation, cube, 0. And I'll forget the time order in a moment. Okay, so the first factor can only be phi minus. I mean phi plus, because phi minus annihilates the vacuum. The last one can only be a phi plus. And now we've got this guy and 2 of those. And so what we've got is effectively phi plus plus phi minus cubed. All right, so, whoops, this is a minus. And so what we need is we need 1 phi minus, takes that one out, 1 phi plus takes that one out, and then we've got 1 left over. And it either creates or annihilates, and so we get 0. So that's basically I guess it was, I should have gone with a majority. All right, anyway. So what we've got left then is this term. And now if we look at this term, and we stick in phi plus plus phi minus, what we see is that this thing turns out, well, there's a theorem due to an Italian named Wick. Wick's theorem is, I don't understand how Wick is an Italian name though, but in any event, Wick's theorem tells us that you can take a time-ordered product of free fields and write it as a normally ordered product of free fields plus a sum of all possible contractions. And a contraction means that, for example, you take this field and one of these, and this field and one of those, and then two of these guys with two of these guys, and in each case you're surrounded by vacua in such a way that you just have a product of Feynman propagators. In other words, you arrange for, let us say, the particle created by one of these phi x's to be annihilated by the phi of x1, and the phi of x2 is going to, and because it's time ordered and you're integrating over various times, this thing happens, in one case, this guy annihilates the particle that phi of y created, but when phi is lated, phi of y is annihilating the particle that phi of x2 created, and so forth. These things are just Feynman propagators, and the pairing of them like this is called contraction. You can contract in any possible way, and you have to sum over all the contractions, you integrate over x and y. That's Wick's theorem, and it's proved in an appendix to this chapter. On the other hand, if you just, for practical purposes, you just look at any particular scattering amplitude that you're calculating, and you get to this point, and you just figure out what is going to happen, and normally you don't have things quite so complicated, although I guess maybe you do. But, well, not, anyway, depending on the theory, when you have charged fields, things are a little bit simpler because you contract, say, psi bar with psi, you don't contract psi with psi, and so forth. All right. Now, just let me remind you that zero time-ordered product, phi of x, phi of y, this is the Feynman propagator df of xy. Schwartz writes this as dxy, and numerically it's d fourths, or d fourth k, 2 pi to the fourth, I over k squared minus m squared, plus I epsilon, and then a phase factor e to the I k x minus y. By the way, that k x minus y is the action to get the particle have going from x to y. Okay, so in this expression, the very first term is d12. And what's the next term? That's d12. This is 0. What's this? Well, the key thing in here is, here, let's do it this way. 0 time-ordered product, phi x1, phi x2, phi x, phi x, phi x, phi y, phi y, phi y. Time ordered ends 0. Okay. What can happen here? Well, you can do dx1 with, you can contract these two guys, and that'll give you d12. But now each of these guys can contract with any of these. So that's 3 times 3. So that's 9 dxx. And then we can have one of these contract with one of those, and actually that's the other 3. So one of these with one of these is 3, and then one of these with any one of these is 3, and then there's one of these with one of those, and that's dyy. So altogether it's 9. And then there's a term that's 6 d12 d cubed xy. That's when x goes with y, and now we contract every x with every y. So the first one has 3 choices, the second one has 2 choices, so you get 6. I don't think it makes sense to write down the rest of that formula. I'll just say plus dot dot dot, and the last term is 18 d1y d2x d squared xy. You can read it in the book there. And then you have to integrate over d4th x, d4th y. And so what you get then is time-ordered product. And now, I guess since I've been in free field land for so long, I'm going to have to write fully interacting under that. Because, okay, so what is it? It is a ratio of, up in the top, what do we have? We have d12 minus g squared integral d4th x, d4th y. And then these terms turn out to be 1/8. That's because each g had a 3 factorial, so you've got 6 squared there, 36. Okay, 1/8 d12 dxx dxy dyy 1/12 d12 dxy cubed. I'm just going to say plus dot 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 for the moment. But that's just the numerator. Now what's the denominator? The denominator is the same thing without any d12. Okay. And so the denominator is this thing here. In other words, it would be 1 minus g squared integral d4th x d4th y, and then this square bracket, but without the d12. Okay. All right, this is of course only to order g squared. So you see this is, from the point of view of a human being, this is a nightmare. And it's a double nightmare. Not only is it incredibly infinitely complex because there are infinitely many terms. Well, to order g squared there aren't, but to all orders of g, there are infinitely many terms. And moreover, there are all kinds of divergences as well. So it's even worse than it looks here. However, there is a certain, there is something nice that happens even at this stage, and it's namely that up here, yes.
What kind of a thing is this?
What kind of a what?
A thing is this? Is this a
It's a number. Yeah, this thing is a number here. It's one number divided by another number, and call that a number.
That is in fact how numbers can be defined.
On the other hand, as I said, it's to order g squared, it's complicated. To infinitely order, it's infinitely complicated. But one of the cute things is that this, well, it's time to write this in terms of some diagrams. So let me try to write this in terms of some diagrams. First of all, if we looked at this whole thing and compared it with the Lagrangian derivation of position space, Feynman diagrams, and so forth, of the early part of the chapter, we'd see all the diagrams are the same except for two. The two new diagrams here are XY and X1, X2, and the second one is XY, X1, X2. And these new diagrams cancel. And in fact, this one here, you see, is that one, because it's got D12, that's this. And then it's got this, the x's and y's are just playing with themselves, they're not dealing with the x1 and x2. And so we write it this way, and we say it's a disconnected diagram. It's also called a bubble diagram. And then the second one has three propagators going from x to y. Well, that's this one. And then it's multiplied by D12. And so that's this thing here. But there's no propagator taking an x1 to a y or an x2 to an x or anything. So those are the two new disconnected diagrams. It turns out they cancel. And that's kind of cute. Let me show you how that works. First of all, we can factor the thing up top. In other words, it is, I have to follow my notes here to get this thing straight. In other words, let's think about this whole business. In other words, 0, time ordered. You guys see this as well? E to the I integral Li d4 of x 0. So what do we have? We have this, and then which is 1. In fact, let me skip a line. 1 plus IG over 3 factorial squared times a half an integral d4 of x, d4 of y, and, well, I'm just giving you the denominator. Well, I shouldn't have done that because I already gave you the denominator. I already did the thing. All right, so this, so you wonder, what is the denominator here? The denominator is this thing, and this turns out to be 9 dxx, dxy, dyy, plus 6 dxy cubed plus ... Although it's to lowest order, it actually stops there. So the denominator is actually a little bit simpler. Oh, there shouldn't be a 1, 2 here, if this is the denominator. So I don't, can you, is it an eraser? Yes. So this was a mistake. My left arm is probably pounding when I wrote that. Okay, so what happens as we write this? Well, it's the numerator term, which is d12 minus g squared d12, and then this integral over d4 of x, d4 of y. So these are the extra terms that came in. This is not the whole story. These are just the extra terms. And I'll just write that as square bracket, and I'm factoring out the D12. And now that's divided by 1 minus g squared times the square bracket. Well, if we bring it up, it is 1 plus g squared integral d4th x d4th y times the square bracket. And now, what we've got then is, the answer is this term plus g squared d12 times that, but then that's all times 1. So if I write it out, the one term gives me d12 minus g squared d12 integral, let me just write it as dx dy square bracket. That's the one term. Then the g squared term, well, on this, it's 0 because it's g to the 4th. But on the first term, it's plus, see, plus g squared d12 integral d4th x d4th y square bracket. So this term exactly cancels that. It turns out, mercifully, that this always happens. In other words, these bubble diagrams always cancel, and they're canceled because of the denominator. In other words, this term here that when I first wrote down, you probably thought, oh, he's building the lily. No, actually, this term is really good because it cancels all kinds of things we didn't want up there. All the bubble terms cancel. Do I owe anybody you learned several, you know?
No, thank you.
I think you just start building next year eventually.
Mine. Community drawings.
By the way, I think I told you the story that Feynman, one semester, he started teaching quantum mechanics in terms of path integrals. And he went on for about 3 weeks, and then he said, you know, path integrals are great, but for some things they're not the best way of doing things. So he went back to the ordinary approach to quantum mechanics. Okay, so let me show you what this is in pictures. It's minus, plus, minus. So these are various diagrams. All that is times so these are just bubble diagrams, and this then is so all the bubbles are this denominator, and consequently the fully interacting time-ordered product, phi of x1, I'll have to write an f here. Okay, if we just have 2, phi of x1, x2. This is then vacuum time-ordered product, the ordinary fields, free fields, phi of x1, phi x2, e to the I integral interaction Lagrangian d4th x time-ordered product 0, no bubbles. Okay. So that's the bottom line then. All those bubble diagrams go away. Now, I could tell you about section 7.2.6, but for no equations, I don't know what I would do but read it. So I just urge you to read it. So just read 7.2.6.
You could audio record it,
I could what?
audio record it,
And we can listen to it later.
yeah.
Should be flat.
All right, now we go to 7.3. And this is what, or close to what one actually does in real life if you're computing Feynman diagrams. In other words, you go immediately to momentum space. So, us look at a particular diagram, T1, and it's going to be x1, x, a loop, y, x2. Okay. And this term is minus g squared over 2 integral d fourth x, d fourth y. Well, this thing here is d1x. This part is dyx2. And then these two guys are d squared xy, dy2. All right, so Schwartz works through this for the massless case, and he chooses the massless case just to simplify the notation. If you want to put in the m squared, it's no problem. In fact, that's kind of like the standard model, you know. You have basically gauge interactions, and then you stick in the masses. How? Well, by a Higgs mechanism. And one part of the Higgs mechanism is very nice, the part that gives the W and the Z their masses. The other part that gives the fermions their masses, that's got to be improved somehow, because you just dial every constant. If you have 8 masses, you just bring in 8 arbitrary constants and fit the masses. Okay. So, in other words, we're going to be using dxy is integral d fourth p 2 pi to the 4th I over p squared plus I epsilon e to the I p x minus y. So we're just going to be using this, and we're going to take this formula and we just stick it in here 4 times. So what do we get? We get that T1 minus g squared over 2 integral d fourth x, d fourth y. Now we've got integral, well, d fourth p1 2 pi to the 4th I over p1 squared plus I epsilon, and then this is repeated 3 times. So we get d fourth p2 I over 2 pi to the 4th p2 squared plus I epsilon dot 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 d fourth p4 I over p4 squared plus I epsilon 2 pi to the 4th, and then the case of 3. But then there are the phase factors, and these are important. We've got here, first of all, e to the I p1 x1 minus x, e to the I p2 y minus x2, e to the I p3 x minus y, e to the I p4 x minus y. In any of these cases, you can flip the sign of this 4 vector, or you can flip the sign of the x1 minus x2. And This is at least, this is for this theory of real scalar field. Okay, well, of course, Dirac posthumously helps us out. The d4 of x here, we've got an x here, an x there, and an x there. That gives us one delta function. Then we've got d4 of y, and we've got a y here, and a y there, and a y there, so we get two delta functions. And so what we get at this stage is minus g squared over 2 delta 4 of p3 plus p4 minus p1 delta 4 of p2 minus p3 minus p4. We get a 2 pi to the 8th from the delta function formula. And then we've got a product I equals 1 to 4 d4 pi 2 pi to the 4th I over pi squared plus I epsilon. And then we have the remaining things that we didn't integrate over, namely the x1 and x2. And so that gives us e to the I p1 x1 minus I p2 x2. All right. So this is sort of simple in a way. Let me try to erase this. All right, so let's do the P3 and the P4 integrals using the delta functions. And so that gives us minus g squared over 2 integral e to the I p1 x1 minus I p2 x2. And then we have I over p1 squared plus I epsilon, I over p2 squared plus I epsilon. And p4th p1, 2 pi to the 4th, p4th p2, 2 pi to the 4th. I don't know what's the matter with this chalk. Okay, now when we do the p3 integral, this thing basically sets P3 equal to P1 minus P4. So this next term here is I over P1 minus P4. That's what P3 is, squared plus I epsilon. And what we have left is delta 4 of P2 minus P1, period, because what's left, you see, is we said that P3 had to be P1 minus P4. If we set P3 equal to minus P3, then is P4 minus P1. So this becomes just delta of P2 minus P1. So that's where this came from. And then we have P4 over P4 squared plus I epsilon. And for some reason, Schwartz replaces P4 by K. And so this thing then gets the appearance of P1 minus K, K squared, D4th K. All right. All right, now what can we say next? Well, now let's take
Okay, we're almost out of time. Let's remember that the S matrix elements are what? It's, for this particular case, it would be minus I integral d4th x1, and it'd be box plus m squared. We're going to integrate by parts, and that'll just pull down a p1 squared with a minus sign. Either minus I p1 x1 minus I d4th x2 the I, well, this is p initial, p final x2 p final squared. So this is the LSZ formula. Okay? And that is acting on omega t of phi of x1, phi of x2, omega. But on the other hand, that, we're going to look at this term of that. There's more, but we're just going to look at this one term. So we're going to reduce this to minus I times minus I is minus d4th x1, d4th x2, e to the minus I, pi x1, pi squared, e to the I, pf x2, pf squared, t1. Now all we're going to do is put in t1, and to save time I'm just going to grab the thing from here, and that will give us minus g squared over 2, e to the I, p1 minus p. All right, I've skipped a line, so I've grabbed the two phase factors and stuck them inside here. And so this is p1 minus pi x1, e to the I, pf minus x2, no, minus p2, x2, and what's left is d4th p1, d4th p2, d4th k, and I'm just going to write that as 2 pi to the 12th. And then it's I over p1 squared, I over, I'm leaving out the I epsilons, I over p1 minus k squared, I over k squared, and then 2 pi to the 4th, delta 4th of p1 minus p2. Well, what happens here? First of all, the integral over dx1 and dx2 gives you two delta functions. That sets p1 equal to pi, and p2 equal to pi, so we immediately can do the p1 and p2 integrations. And let me give you the bottom line, since we're essentially out of time, and I'll redo this at the beginning of the hour, or maybe it makes more sense to just write it as g squared over 2 integral pi squared pf squared delta 4 p1 minus pi delta 4 pf minus p2 2 pi to the a d4th p1 d4th p2 d4th k 2 pi 12, and then I over p1 squared, I over p2 squared, I over p1 minus k squared, and I over k squared, and then oh my gosh, 2 pi to the 4th delta p1 minus p2. It never ends. Without Dirac, we'd be dead completely. Okay, you do the p1 and p2 integrals,
And then that, what does that mean? That means that the pi squared and pf squared are the same thing as p1 squared and p2 squared, so they cancel. And what we wind up with is minus g squared over 2 integral d fourth k over 2 pi to the 4 I over pi minus k squared plus I epsilon, I over k squared plus I epsilon, and then 2 pi to the 4 delta of pi minus pf. So the first thing is that the external legs cancel. That is, those two guys cancel. And then what we've got left is this thing. And one, so we've got pi, and then this is, let me just look at it, pi k, pi minus k, if we think of all both of them as like that, and then pf. And so that's the Feynman diagram, and that Feynman diagram then takes this form, and altogether it looks like this. S is equal to 1 plus 2 pi to the 4 delta function of the momenta, and then Im. So what we've computed essentially is that, apart from the 1. All right, I'm sorry to have gone over a little bit. Let's, any questions? All right, let's quit.